Hi everyone. In today's video, I will be going over the Unit 6-2 study guide. So, our first problem here, we are given three different numbers written in complex form, and we're going to do multiple things with them. So, these are going to get reused as we go for the first few problems. If you haven't already realized that, you will in a moment. So, the first question just asks us to identify which quadrant they are in. I'm going to actually full-on graph all three of these because that will be helpful later anyway. So, and it'll help me answer the question better. So, for part A, we have the three given numbers. Z1 is 5 minus 2i. Z2 is negative 2 plus 6i. And Z3 is 1 minus I. Okay, so the first question is which quadrant they are each in. And the easiest way to answer this question is just to graph them. And again, I'll need the graph anyway for later, so might as well do it. All right, when I'm graphing this, it doesn't need to be the most perfect, accurate, beautiful graph you've ever seen. Really, the point of the graph is to just get a picture that you can work with. Okay. So just graphing the points for now, and then I'll add to each picture as I go. 5 minus 2i. When you graph these, it's just like graphing like an xy coordinate, but instead this is a and b. And so a is like your x, and that's also the real axis, and then your b is like the y. This is the imaginary axis. Just a quick refresher. So we graph this like normal, so this would be right 5 and down 2. And again, this is not going to be a perfect, most accurate dimension, just to the best of your ability. Just for like freehanding something. So something like that. Okay, number 2, or second point, we have negative 2, positive 6, so we go left 2, up 6. And then 1, negative I. This is like a negative 1. So this is right 1, down 1. This one I'm going to exaggerate the size a bit just because I want a picture to work with later. So I like went down and or right and down the same amount, but obviously I did not do 1 necessarily. Okay, so the first question is which quadrant they are in. It's pretty well answered that. Z1 is in quadrant 4. Z2 is in quadrant 2. And then Z3 is again in quadrant 4. Okay. Problem number 2. Find the absolute value, that's also referred to as the modulus of each complex number. So that's what we're asked to do next. And again, having a picture really helps us to do this. So I will write it out. So we need to find the absolute value of 5 minus 2i. The absolute value of negative 2 plus 6i. And the absolute value of 1 minus I. And then reminder, we refer to this same thing as R in our picture. So let's add to our picture now. So the most important line to draw here is from the origin directly to the point you drew. This is our diagonal, and this is what we refer to as R. Put that here. Let's put it in the wrong spot. So this is what we are looking for. Ignore that. And then we draw our triangle from our point to the x-axis, wherever that is in the quadrant. So this will go up to meet the x-axis. For our second drawing, it will go down to meet the x-axis, and again up to meet the x-axis. And then if it's helpful to your drawing, label the sides. So for our first triangle, this was right 5 down 2. So this had a 5 and -2 for its side lengths. Second picture, this was left 2 up 6. So -2 and +6. And then our last picture, this was right 1 down 1. So 1 and -1. So when they ask us to find the absolute value, the modulus, we are really looking for our R value. And that is simply just with Pythagorean theorem. And all of these take the same form. A squared plus B squared equals R squared. R, as you can clearly see, is the hypotenuse in every situation. So A and B, which are also the numbers from the complex, go in there like so. So for our first problem, we have 5 squared plus, this is B is negative, so take care with that. Make sure you put it in parentheses, it should come out positive. 5 squared -2 squared equals R squared. We get 25 plus 4 equals R squared. 29 equals R squared. And then don't forget to square root both sides to get that R is equal to 29. Square root of 29, excuse me. So that's our answer for number 2, for the first number on number 2. This radical can't be broken down, so we leave it. On the test, if you have a radical that you can break down, you do need to do it. All right, let's repeat that for the second number. A squared plus B squared equals R squared. So again, it's just your 2 numbers in the complex number that go in for A and B. -2 squared plus 6 squared equals R squared. That's 4 plus 36 equals R squared. That's 40 equals R squared. Square root both sides. Square root of 40 is equal to R. Now the square root of 40 can be broken down, so this is one where I would be required to break it down. There are many ways to go about it. You can simply use the factors of 40 and then break it down into smaller and smaller factors and then create groups. The best thing you can do is identify 2 numbers that will give you 40 when multiplied, and one of those numbers being a perfect square. So that would be 4 and 10 for this problem. And then I just break these down individually into their factors as long as I don't use 1 in the number itself. So 4 breaks down into 2 and 2. The 2's can't break down further, so I'm done there. And I'm going to cross out the 4 since I broke it down. Now the 10, that breaks down into 2 and 5. So this is what I have left over. So if you can make a pair of numbers, the same number, then that comes out of the radical as just that. So this becomes just a 2. And then the 2 and the 5 are still left over, and these aren't the same, so they can't come out of the radical. So we're going to put them back together. So this is square root of 2 times 5. And then if I put that all together, I end up with 2 square root of 10 equals R. So pretty much I didn't need to end up breaking down that 10. It didn't really give me anything, but it's okay if you do. So that is what the simplified radical is for that problem. There is a very easy way to check this answer, by the way. If the square root of 40 and 2 square root of 10 represent the same number, then their decimals will be equal. So if you break it down and you're not sure you did it right, put these both in the calculator and make sure they come out the same. So there's the square root of 40, and then this is 2 square root of 10. So this is how you know that your breakdown was done correctly. Very easy to check. Okay, one more time. A squared plus B squared is equal to R squared. This time A and B were both 1s, B being negative. So we have 1 squared plus negative 1 squared equals R squared. Take care to get rid of the negative. That becomes a 1 plus positive 1 equals R squared. 1 plus 1, we all know that's 2. And then square root both sides. R is the square root of 2. Clearly 2 does not break down further besides 2 and 1, so that is our final answer. So this is the modulus slash absolute value slash R value of all three of those numbers. That will come in handy very shortly. Lastly, number 3. Find the argument of 5 minus 2y, so just the first number. So I'm going to continue this on the same paper. So find the argument, and the argument is the same thing as theta of z1. So let me return to my drawing and add more to it. To help us visualize this process, it's very helpful to graph theta and alpha into your picture. So theta starts at the starting point, so where the unit circle would be 0. And it goes all the way around until you hit the R line that you draw. So this is theta. Alpha is always inside the triangle. Here's my alpha. So the argument process, you find alpha and then you use alpha to find theta. And this always looks the same on these problems. For this, we use SOHCAHTOA, and because we're always given these two sides of the triangle, these would be the opposite. This is across from the alpha. That's my O. And then my adjacent, it touches the alpha. Obviously, the R is the hypotenuse. Since I'm given the opposite and the adjacent, I'm going to use the tangent function. Tangent of alpha is equal to O over A. And again, this is how it's going to be set up on all of these problems because we're always given the O and the A on these problems. So you're always going to use tangent. There's not been a time where we've used sine or cosine. So filling in, we have tangent of alpha equals O is negative 2 over A is 5. And then we use our calculator to get the answer. Alpha equals, we take the inverse tangent of both sides. Inverse tangent. Now something that's really important to remember when you go to do this problem, if you have a negative like I do here, you need to turn it into a positive. So this is positive 2/5. The reason we do that is we find our alpha value. Alpha clearly is a small angle. It has to be smaller than 90 to be exact. And all of our 90 degree, anything smaller than 90, exists in the first quadrant. And so if we want the right answer, we got to make sure it's positive. So we send it back to quadrant 1. If we do a negative, we might get something else we don't want. So, calculator to get our answer. So, inverse tangent of positive 2/5. And for this one, I just went out to the 10ths place. So, 21.8. So, that's my alpha. Now, a reminder, I'm looking for theta, which is not the alpha. I'm looking for the argument. So if I come back and label this in my drawing, I know this alpha is 21.8 degrees. And then you can either memorize the quadrant rules for all 4 quadrants, or you can just use the picture to know, based on how this is drawn, what my calculation is to find theta. Notice if I put alpha and theta completely together, then I end up with a complete circle, which is 360 degrees. So if I take the full circle, which is 360, and I remove the alpha, the leftover portion is theta. So the calculation for theta in this problem is 360 minus our alpha So 360 minus 21.8. And when I do that, that is going to leave me with 338.2 degrees for theta. I'll add that to my drawing. So that is the value of our theta, of the argument. Now just a quick note, if you want to memorize the rules for each quadrant, here is what they are. We'll do this quickly. Hopefully by this point you've picked up on these rules, like you agree, you can see why they are the way they are. But with practice, you do notice that these rules always work for each quadrant. So for the first quadrant, theta is equal to alpha. For the second quadrant, theta is equal to 180 minus alpha. For the third quadrant, theta is equal to 180 plus alpha. And lastly, the fourth quadrant is what I just did. Theta is equal to 360 minus alpha. So if you want the rules complete for each quadrant just to memorize, you can do that as well. All right, next problem, number 4, and that's going to be under section B. Now we're still going to reuse some of these, so I'm going to keep my paper handy. Okay. Section B, write in trig, that's also polar form. Come on, focus for me. There we go. Write in polar form, and we give you the polar form. By the way, we will do this on the test. We will write in the problem, this is what your answer should look like, so at least we give you that. So all of these are written in complex form, and we want them to look like that. So for all of these problems, in order to get it to this form, you have to know r and theta. The good news is for all the first 3, so 4, 5, and 6, Z1, Z2, Z3, these are repeats of the ones in A. We already know all 3 R values, and we know the theta, the argument of number 3, of the first of Z1. So we can actually do number 4 extremely quickly. And then 5 and 6 will only take a moment to find their theta values. So number 4 specifically asks for the polar form of Z1, which again was 5 minus 2i. And to put it into polar form, we have, it's r cosine of theta plus I sine of theta. So clearly we need to know r and theta, and we actually do already know both of these values for this number. We found that r is the square root of 29. That was number 2. And then we found in number 3 that theta is 338.2 degrees. So this is a very quick one to answer. So we just fill in our values. We have the square root of 29 times cosine of 338.2 plus I sine of 338.2. And that's our answer. And again, we give you the format for this. That's in the directions. So you don't have to memorize that part, but obviously you do have to know how to find r and theta, also known as the modulus and the argument. All right, repeat that for 5 and 6. 5 and 6, we will have to find our theta before we can proceed. So number 5, again, we want polar form of Z2, which was -2 plus 6i. So again, we need r and theta. So r we found to be 2 square root 10. Theta is to be determined. So let's look back at the drawing we made for Z2. Again, theta, you start at the starting point of the unit circle, which is on the right side of the x-axis, and you draw up to that r line you drew, and that is theta. And then from the r line to the x-axis, to the nearest x-axis, that's your alpha. It's itty-bitty inside the triangle. Find alpha, we can find theta. So once again, it will always be the same. We're going to use that tangent of O over A, or tangent equals O over A. So tangent of alpha equals O over A. Tangent of alpha equals 6 is the O, it's opposite the alpha. -2 is adjacent, it touches the alpha. So 6 over -2. And then clearly that is 3. -3, but then remember, we do need to turn that into a positive if we're going to actually work with alpha. So, alpha is inverse tangent, because remember, we just take the inverse tangent of both sides, so inverse tangent of 3. Alpha is approximately again, let's take it out to the tens place. 71.6 brings the 5 up to a 6. So 71.6 degrees. And then from here, we already discussed the rules for each quadrant. If I put the theta and the alpha together here, this creates a half circle. We know that's 180 degrees. Go ahead and add this, 71.6 degrees. So if I take the half circle 180 and I take out the alpha part, I get my theta. So we have theta equals 180 minus alpha, 180 minus 71.6, and subtracting, we get 108.4. So theta is 108.4 degrees. And now we just put it all together. Let me move this so you can see the form once again. R cosine theta plus I sine theta. So R was 2 square root of 10 times cosine of our theta was 108.4 degrees plus I sine of 108.4 degrees. And again, just leave your numbers as they are. Don't multiply anything. Don't configure anything. This is how it should look. All right, we're going to do that one more time for number 6. Polar form of Z3, and Z3 was 1 minus I. We already found the r value earlier. That was the square root of 2. Found the answer in number 2. And then we have not found the theta yet. So again, I need to repeat that process I just did a moment ago. So let's add to our picture. Theta again starts at the starting point and goes around till it hits the r line. That is theta. Alpha is the bit that's inside the triangle. And then we're going to use tangent. So we need our O and A. -1 is the O, +1 is the A. For this problem, it wouldn't matter if you mix them up because they'll both end up being positive. Okay, so we have tangent of alpha equals O was -1 over A was +1. And then again, this needs to be a positive number if we're going to find alpha. Tangent of alpha is equal to +1. Inverse tangent on both sides to get alpha. Alpha is inverse tangent of 1. You can use your calculator for this, but I'd hope some of you already have memorized where tangent is equal to 1 on the circle. That is at 45 degrees. So this one's a nice number. So if I go back, we now know that this alpha is 45 degrees. And then we've already done one in the fourth quadrant. So we know theta is 360 minus the alpha. So theta here, 360 minus alpha, 360 minus 45, and that will give us 315. So 315 degrees. And then we fill it all in. So we have r, that's the square root of 2, times cosine of our theta, which is 315, plus I sine of, again, our theta, which is 315. And that's our final answer. All right, next, number 7. This is a completely new number we have not been given yet. So I'm going to do the entire process start to finish. I have to graph it, find r, find theta, put it all together. So I am going to start this on a new page. Number 7, polar form of z4, which equals 1/2 minus rad 3 over 2i. So we have to do the process start to finish because we don't know the r or the theta yet. So the first goal is to uncover r and theta. Once we've done that, we're pretty much done with the problem. We just have to put it all together into polar form. First things first, we'll make a small graph. Now these are fractions, so I'm very obviously going to exaggerate their measurements here. This is right 1/2 down rad 3 over 2. Something like that. So I'm going to draw from the origin out to my point. That's my r. And then this was right 1/2 and down rad 3 over 2. And then I'm going to go ahead and draw an alpha and theta as well. I will need those later. So there's my theta. Alpha is inside the triangle. Okay, so first we have to find r. Again, we use the Pythagorean theorem, a squared plus b squared equals r squared. R is clearly the hypotenuse here. A squared is 1/2 squared plus b is negative rad 3 over 2 squared equals r is still just r squared. So again, your a and b, yes, the same a and b that are in the complex form. Conveniently enough. Squaring, remember this is a half times a half, so you're going to square the top and the bottom. This becomes 1/4 plus negative rad 3 squared, that's going to become positive 3. You multiply this by itself, you get a 3, and obviously squaring turns a negative to positive. 2 squared is 4. 1/4 plus 3/4, that is 4/4. And we know that's 1. And then the square root of 1 is just itself. R is 1. So, R is 1. Theta, the argument. Once again, we start by using that tangent formula. Tangent of alpha is equal to O over A. O is opposite or alpha. O for opposite. And then the other number will be our adjacent. It touches the alpha. So we have tangent of alpha is equal to negative rad 3 over 2 over 1/2. Clearly we can flip this, but a quick trick is if you have the same denominator, when you have a fraction over a fraction, if the denominators are the same, those will cancel. So that becomes tangent of alpha equals negative rad 3. And then inverse tangent on both sides. Don't forget to turn this back into a positive before you do that. Alpha equals inverse tangent of the square root of 3. And this is actually a really nice number. I believe it's 60, but I'm going to check myself just to be sure. Inverse tangent of the square root of 3. 60. Alpha is 60. So in our picture, we have 60 degrees. And again, we know theta in the fourth quadrant is the full circle 360 minus the alpha. (360 minus 60) gives us 300. So theta here is 300 degrees. Now, it does take practice to notice things like this, but this is actually a problem that we could have very quickly done a shortcut, at least to find the theta, if you notice it. So our point here was 1/2 negative rad 3 over 2. So let me write that down. So like this. Those numbers should look familiar. They belong to the unit circle. So had you noticed that from the beginning, we could have skipped this work and gone straight to the unit circle and found that point, which is right here. And we would have found that it was 300 degrees. That's our theta. And then if you remember, this is called the unit circle because the r, the radius of all of these, is 1. So you very quickly could have done that instead. So that is a shortcut if you realize that your problem is a special. So keep your eye out for those. But if not, it was very good practice to do all this work, whether you agree or not. Okay, we are basically done. Remember, the goal is to get this into polar form. That's why we found all of this, so let's do that. Once again, that looks like this. R cosine of theta plus I sine of theta. R is 1. Cosine of 300 plus I sine of 300. And in this case, the better answer would be to drop the 1, since clearly, if it's a 1, we don't need to write it. cosine of 300 plus I sine of 300. And that turns out that way again because this is a special angle. It's on the unit circle. So of course it's r, the radius will be 1. All right, I believe that was all for those, yes. Now we're going to switch to more the quicker types of problems. All right, number 8. Rewrite in standard complex form. These are my favorites. They are very quick problems. Now we're going the other direction. We start with polar form and we end up in complex form. So number 8. 3 cosine of 120 plus I sine of 120. So the protocol for these problems is to first evaluate what these are on the unit circle. If they're not on the unit circle, then you will use your calculator and round. So let's look at the unit circle at 120. So 120 is right here. And as you can see, cosine is -1/2. And then sine is rad 3/2. And then bring down the rest of the symbols. And then you can put the I in front, but let's go ahead and put it in the back because that's where it's going to end up at in the end. So reminder, because this number on the right side has an I and this one on the left does not, you cannot add these. Please don't do that. So the only other thing we have to do is distribute the 3 into there. Now reminder, this is like a 3/1. So when you're multiplying, you're only multiplying by 3 on top of the fraction, not on top and bottom. When I do that, that's going to be -3/2 plus 3 rad 3/2I. There's no reducing to do here, so I am done. That is my answer. That was number 8. Let's do that again. Number 9. Number 9 says 2/3 cosine of 7 pi over 4 plus I sine of 7 pi over 4. So once again, the first step, you take out your unit circle and you find what those are on the unit circle. 7 pi over 4 is over here in quadrant 4. And we get, my blue, there you are. Cosine is rad 2/2, and then sine is -rad 2/2. I'm going to go ahead and put the I in the back, bring down the plus, and bring down the 2/3. So this is what we end up with. And again, the only thing to do from here is to distribute. Now in this case, I will multiply the tops by 2 and the bottoms by 3. So you can do some canceling as you go if you want. I will wait till the end to do that, but if it were me personally doing it, I would go ahead and cancel out some things. This becomes 2 rad 2/6. Plus 2 times -rad 2, so -2 rad 2 over, again we have 6I. We know that 2/6 reduces down to 1/3, so this becomes rad 2/3. I'll go ahead and bring this minus out here, so it's just a minus this number. Again, it reduces down to 1/3, so rad 2/3I is my final answer. All right, I've got one more of those. Number 10. Number 10 says 4 cosine of 65 plus I sine of 65. So first thing we need to do is evaluate what these numbers are. I'm going to go ahead and tell you these are not on the unit circle, so we will use our calculator to get an answer. We aren't given any specific rounding instructions on this particular problem. Elsewhere on the study guide, we've been asked to round to the nearest tenth, so you can just kind of use your judgment here. There will be rounding instructions on the test for you to follow. So in that case, I'm just going to go ahead and round to the 10th to be consistent. That would give me 0.4 for cosine. And then for sine, that would give me 0.9. And then don't forget there's an I attached to that 0.9. Bring down the plus, and then we have 4. Only thing left to do is to multiply because we can't add those numbers inside. They are not like terms. So 0.4 times 4, that should be 1.6, yes. 1.6 plus 4 times 0.9, that is 3.6i. We'll check those just to be sure. Yes. Again, we can't add these here. They are not like terms, so we are done. And again, those answers should match. If we look back at the directions, the complex form of a plus bi, which we clearly do have in all 3 of our answers. So we are done. All right. Next few, we're going to be multiplying and dividing our polar form numbers. And we're going to do the both, multiply and divide on both of the problems. So, number 11. We have z1 equals 5 cosine of 50 plus I sine of 50. And z2 equals 6 cosine of 20 plus I sine of 20. So we're asked to multiply and divide these. And I will write those formulas out up here just as a reminder. So if we have, this is going to be in a general form, and feel free to skip this part if you know how to do it or what the formula looks like. This is going to take me a minute to write out. If our first number, we have R1 times cosine of theta 1 plus I sine of theta 1. And we have R2 cosine of theta 2 plus I sine of theta 2. Then when we're multiplying, it looks like this. R1 times R2 times cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Now, clearly you don't have to have the full formula memorized, but you do need to know what the calculations are. So basically you multiply the two r's together. That will get you your new r value. And then you add the theta values together and put them in with cosine and sine. And then dividing, you're going to do the opposite. Divide, yeah. It's like, why does that look weird? That is not how you spell it. Okay, yep, divide. All right, R1 divided by R2. And then instead of adding the thetas, we subtract theta 1 minus theta 2 plus I sine theta 1 minus theta 2. And in this case, since we have subtraction, the order of the thetas absolutely matters in the formula. So make sure you do subtract correctly. Okay, so those are handy. Now we can follow those. So we have to multiply and divide here. Those are the directions. Multiplying on number 11. If it's not clear, we have R1 and R2, and then theta 1 and theta 2. So multiply R1 and R2, that's the first step. 5 times 6, that gives us 30. Cosine of, we add the thetas, 15 and 20 is 70. And one last thing you need to do is just check and make sure your angle isn't too big. We do have the condition here. Theta is greater than or equal to 0, so it can be 0, but it's strictly less than 2 pi, which is also 360 degrees. So it can't equal this number because that is 0 on repeat. So we have to make sure our angle is in this range. And clearly 70 is, so we're good. So next so that's the multiplying. And then the divide. You divide R1 by R2. Again, order matters here, 5 over 6. Can't reduce that, so we're good there. And then cosine of theta 1 minus theta 2, 50 minus 20, that is 30. And 30 is in the range, so we're good here. And that's it. So that problem required very little work. All right, so let's do that again for number 12. Number 12, we have z1 equals 2 times cosine of 130 plus I sine of 130. And z2 equals 3 times cosine of 280 plus I sine of 280. So we multiply and we divide. Multiply first. R1 times R2, 2 times 6, that's going to give us, 2 times 3, that's going to give us 6. And then 130 and 280, I believe that's 410, but I'm going to check myself. So remember, we add the thetas. So this is cosine of 410 plus I sine of 410. Now, 410 is bigger than 360, the maximum allowed angle in the range. So we are going to have to find a smaller angle. So we do this by subtracting 360, a full circle, from 410 to see where this would actually land on our unit circle. So minus 360, and we end up at 50. So my new answer is 6 times cosine of 50 plus I sine of 50. And this is the acceptable answer for this problem. Divide. First, we divide our R values. So this is 2/3 times cosine of 130 minus 280. Make sure you do it in that order. I believe that's negative 150. Yep. Cosine of negative 150 plus I sine of negative 150. Now, again, our theta has to be bigger than or equal to 0, so a negative is not allowed. So this time what we need to do is add 360 to negative 150. So we keep going around the circle in the forward direction until we end up at a positive value. So let's add 360. and we end up at positive 210. So this is going to be my angle, my theta. Cosine of 210 plus I sine of 210. That is my answer. All right, 13 and 14, we're going to do that again, but in radians. Z1 equals 2/3 cosine of 2 pi over 3 plus I sine of 2 pi over 3, and Z2 equals 15/12 cosine of 3 pi over 4 plus I sine of 3 pi over 4. And once again, we're asked to multiply and divide. So first we multiply. So we multiply the r's together. So this is 2/3 times 15/12. I'm just going to write it out first and foremost. Oh my goodness. 2/3 times 15/12. And then I'll do the math for the next step. Cosine of 2 pi over 3 plus 3 pi over 4, we add the thetas, plus I sine of 2 pi over 3 plus 3 pi over 4. And then we multiply the fractions, multiply straight across top and bottom. We get 30 over 36. Cosine of, we need a common denominator here. So clearly our common denominator is going to be 12. 3 and 4, we can get 12. So we multiply the left fraction, top and bottom, by 4. So times 4, we get the 12, and then we get 8 pi. And then the right fraction, we multiply top and bottom by 3. 3 times 3 pi, we get 9 pi. Plus I sine of 8 pi over 12 plus 9 pi over 12. From here, we just simplify. So clearly we can reduce this fraction. We can reduce it by 6. Divide top and bottom by 6. You end up with 5 over 6. Cosine of, we add 8 pi and 9 pi together, and we get 17 pi over 12 plus I sine of 17 pi over 12. Now 17 pi over 12, this seems a little big, so you do want to make sure that this does fit into the range. Remember, our range is up to 2 pi. So for this problem, 2 pi, if I'm out of 12, that would be 24 pi over 12. Because if I reduce this, I do get 2 pi. 17 pi over 12 is not too big, so we're good. All right, now we have to divide. So this time we're going to divide our R numbers. So for the first step, I'm just going to write it out like I did before. 2/3 divided by 15/12 times cosine of, we subtract our thetas in order. 2 pi over 3 minus 3 pi over 4 plus I sine of 2 pi over 3 minus 3 pi over 4. So for this, we keep change flip. You keep the top fraction the same. 2/3, change division to multiplication, flip the bottom fraction. So this becomes 12 over 15. The good news is, since we've already done this, getting the common denominator one time with these same numbers, they are going to turn out exactly the same, just with subtraction. So cosine of 8 pi over 12 minus 9 pi over 12 plus I sine of 8 pi over 12 minus 9 pi over 12. And then for our next step, we can go ahead and do some multiplication here. This is 24 over 45. Cosine of 8 minus 9, that's a negative 1 pi over 12, plus I sine of negative pi over 12. And then a couple things here. I can reduce this fraction here. Let's see. Looks like it's just going to be a 3. So if I divide top and bottom here by 3, I end up with 8 over 15. And then my negative pi over 12 is not allowed because it's a negative. So if this were in degrees, I would add 360. So I'm going to add 2 pi to it. So negative pi over 12 plus, and we already discussed up here, 2 pi for this problem is actually 24 pi over 12. So I'm going to add that to it to get a positive. So it's just like 24 minus 1, that is 23 pi over 12. So the positive value for that is 23 pi over 12 plus I sine of 23 pi over 12. And there is my final answer. All right, we have one more of those, number 14. Z1 is 10 cosine of pi over 6 plus I sine of pi over 6. And Z2 is 7 times cosine, 15 pi over 6, plus I sine of 15 pi over 6. And once again, we need to multiply and divide. So we'll multiply first. Multiply the r's together, 10 times 7, that is 70. Cosine of add our thetas, and thankfully these both have the same denominator here, so that saves me a little bit of work on this problem. Pi over 6 plus 15 pi over 6 plus I sine of pi over 6 plus 15 pi over 6. 70 cosine of, this is like adding 1 to 15, so 16 pi over 6 plus I sine of 16 pi over 6. I will simplify these. 70 cosine of, divide both of these by 2, 8 pi over 3 plus I sine of 8 pi over 3. Now problem, you always want to check for whether it's greater than the 2 pi restriction, especially if it looks a little too big. It's kind of suspicious. So for this problem, 2 pi equals, if we have a denominator of 3, multiply top and bottom by 3. 3 times 2 is 6 pi. If I were to divide that, I would end up with 2 pi. 6 pi is our restriction. So we need to subtract 2 pi, so 6 pi over 3 from 8 pi over 3 to get our new angle. So 8 pi over 3 minus 6 pi over 3 gives us 2 pi over 3. So that is the allowed number. 70 cosine of 2 pi over 3 plus I sine of 2 pi over 3. Final answer for multiplying. Divide one more time and we will be done with those problems. We'll divide our numbers. So we divide the r's, 10 and 7. So this is 10 divided by 7 times cosine of, subtract your thetas this time, pi over 6 minus 15 pi over 6 plus I sine of pi over 6 minus 15 pi over 6 10 over 7, cosine of, this is 1 minus 15, so negative 14 pi over 6, plus I sine of negative 14 pi over 6. I'll go ahead and simplify that fraction. 10 over 7, cosine of, divide top and bottom by 2, negative 7 pi over 3, plus I sine of negative 7 pi over 3. Again, you are not allowed to have a negative, so we're going to add 2 pi, which in this problem is 6 pi over 3. So we'll add 6 pi over 3 to get our new answer. And that won't make it, not quite. We end up with negative pi over 3. So if one time doesn't do it, you're just going to do it again. Negative pi over 3 plus, we'll add 6 pi over 3 again. We're adding a full circle each time, going around and around until we get the number that is on the unit circle. This will give us 5 pi over 3, what we need. So we have 10 over 7, cosine of 5 pi over 3, plus I sine of 5 pi over 3. And that is our final answer. Next, we have de Moivre's theorem. And this is section E. I've kind of abandoned the lettering at this point. Oops. More than likely, this was your favorite to do in the unit because it is extremely easy to remember and easy to use. So here is how de Moivre's theorem goes. We have r cosine of theta plus I sine of theta, all raised to the nth power. And when we have that, we can simply move the exponent and we can do this. R to the n times cosine of theta times n plus I sine of theta times n. So these are very quick problems. Number 15. For cosine of 15 plus I sine of 15, all raised to the third power. So that's going to give us 4 cubed. Cosine of 15 times 3 is 45, plus I sine of 45. 4 cubed is 64. 64 cosine of 45 plus I sine of 45. Now make sure you keep the operations organized in your mind. So the r in front, it treats it as the exponent. The theta's inside, you just straight up multiply the numbers. That would be something that's very easy to confuse. Okay, let's do that again. Number 16. Square root of 2. Cosine of 150 plus I sine of 150. All raised to the 4th power. Square root of 2 to the 4th power times cosine of 150 times 4 should be 600. Yes. Cosine of 600 plus I sine of 600. Now let's talk about the square root real quick. You can type this into the calculator. I will do that. But I'm going to show you on paper how this works out, because in a moment you will need to know how that works to get a different answer. So you get 4. Now let's go over this on paper, because it will show up a different way in just a moment. Square root of 2 to the 4th power. That's the square root of 2 times the square root of 2 times the square root of 2 times the square root of 2. And when you have 2 of them, that just becomes 2. 2 times 2 we know is 4. Now when it's even like that, you can nicely put it into your calculator and get the answer. When you have a different type of exponent, that doesn't quite work that way. So you need to know the on-paper version, because your calculator will not give you the nice answer. We'll come back to that later. 4 times cosine of, we're not allowed to have 600, so it's too big. So we're going to subtract 600, or subtract 360 from 600 to get back in the allowed range of values. And we bring us down to 240. So 240 plus I sine of 240. And there's our answer. All right, 2 more. 17. One plus I to the 5th. Now, some of you probably looked at this and were a bit confused, because this clearly does not match de Moivre's theorem. But, a reminder, we have already done multiple problems and discussed how we can change our number from complex form, the current form it's in, to polar form, the form we need it to be in order to get our answer. The other option, of course, is writing this out 5 times and getting our answer, which we will still then need to convert to polar form. So even though that sounds easier, it is going to be a lot more work. So let's just go ahead and convert it now and then use de Moivre's theorem to get our answer. So this is going to be a minute. I know this is not fun, but that is what we are asked to do. So to go to polar form, we need our R value. And then we need our cosine. We need our theta value. Plus I sine. Again, we need our theta value. And then that will all be raised to the 5th. So we need to figure out what this polar number is first before we can go anywhere else. So first things first, we graph it. And this one is actually a nice one. How the numbers turn out, it's very nice. Sorry, I didn't even go over it. Right one, up one. Right one, up one. Here's our point. So we have 1 and 1. And then this is our r. And then you know the drill. To find r, a squared plus b squared equals r squared. A and b are both 1. 1 squared plus 1 squared equals r squared. 1 squared and 1 squared, that is going to give us 1. 1 plus 1 is 2. Square root both sides. R is the square root of 2. So r is the square root of 2, we know that now. And then let's find our theta. So again, we use tangent to get alpha, and then alpha to get theta. So when we draw our theta into the picture, you start at the starting point of the unit circle, and you go up until you meet your R line. So in the first quadrant, this looks a little odd. And then alpha is the itty-bitty angle inside the triangle. So notice in this problem, alpha and theta are going to be exactly the same, if you remember the rules from earlier. So once I find alpha, I have found theta. So to find theta, we first use tangent of alpha equals O over A. O is opposite alpha. A touches alpha. Oh, wrong side. A touches alpha here. So 1 over 1. So tangent of alpha is going to equal 1. Inverse tangent on both sides. And alpha is already positive here, or the number here is already positive, so we don't have to worry about that. Inverse tangent of 1, we have actually already had this earlier. If you remember, the inverse of tangent is 1 at the angle of 45 degrees. So in this problem, alpha is 45 degrees, so is theta. Theta equals alpha, so theta equals 45 degrees. So finally, we can fill that in here. All right, now that we have that, we can go ahead and finish the problem. We need to use de Moivre's theorem. So I'm just going to write this out one good time. Square root of 2 cosine of 45 degrees plus I sine of 45 degrees raised to the 5th power. So when we do that, we have the square root of 2 to the 5th power times cosine of 45 times 5 is 225 plus I sine of 225. Now this is what I was talking about a moment ago. We now have the square root of 2 to the 5th. If you put that in your calculator, you're going to get a not nice decimal. And if we want exact answers here, that is not what we're looking for, is that decimal. We want an exact answer. So, square root of 2 to the 5th, that is the square root of 2 multiplied 5 times. Groups of 2 will make just 2. Square root of 2 times itself is 2. And then we have one lonely rad 2 left. Multiply them all together, and we get 4 rad 2. And that is our final answer. Okay, we have one more problem, number 18, and we will be all done. And I think I'm going to be able to cheat on this problem. If I can, I'm going to do it since I've shown you how to. So 18, we are given the square root of 3 minus I to the 6th power. Again, you can't use de Moivre's theorem in the complex form. It needs to be in the polar form. So I'm going to set up what that's going to look like. So we need our R value. Cosine of, we need our theta. Plus I sine, again, we need our theta here. And then that will all be raised to the power of 6 when I'm all done. All right, first things first, we need to graph it. We have a visual. So this is right rad 3 down 1. Right rad 3 down 1. Something like that. Turns out I will not be able to cheat on this problem. This is not as special as I thought it was. This is my R. And I went right rad 3, and then this was a negative 1. Go ahead and draw an alpha and theta. All right, we know the drill. Find R. A squared plus B squared equals R squared. So that's rad 3 squared plus B is negative 1 squared equals R squared. This gives us 3 plus 1 equals R squared. 4 equals R squared. Square root both sides. R is 2. And now we find theta. We need our O and our A. O is opposite the alpha. A is adjacent to it. It touches it. Tangent of alpha equals O over A. Tangent of alpha equals O is negative 1 over the square root of 3. Again, we need to turn that into a positive since we're finding alpha. Alpha equals, you take the inverse tangent of both sides to get your answer. Inverse tangent of 1 over rad 3. And I believe that's 30 degrees. So I'm going to check. Inverse tangent of 1 divided by the square root of 3. 30. So alpha is 30. So alpha is 30. We're in the fourth quadrant. We know that theta is the whole circle, 360 minus alpha. (360 minus 30), 330 degrees. And last but not least, I will apply the theorem. I'm going to bring this down here. 2 cosine of 330 degrees plus I sine of 330 degrees, all raised to the 6th power. And then we have 2 to the 6th times cosine of 330 times 6. 1980 plus I sine of 1980. 2 to the 6th, 64, yes, 64. Now, 1980 is clearly too big, so we're going to have our work cut out for ourselves trying to find the correct angle. So let's subtract 360 until we get there. We're going to do it over and over again. Go back a circle at a time until we get an angle that is on the circle. 180. And that is our final answer for the review. All right, that is all for this video. I hope you found this helpful. I hope I was able to answer any questions you had. If not, feel free to reach out to me in person or via email. Otherwise, I hope you have an awesome day. Bye.